Hi everyone, this is Dr. Anna. This is segment 4 of the rock fossils and time module, and we're going to start talking about the biochemical sedimentary rocks. The first big group we have to talk about is the carbonates. Carbonates mostly composed of CO3 anion with different cations. CO3 anion is a so-called polyatomic anion. See, the CO3 is carbon and oxygen, and that's why we call it polyatomic. And it has two negative charge, which has to be fulfilled with different cations. One of the most common cations is going to be the calcium, and the other one we will have to know, and it will have two positive charges, so it will completely fulfill the two negative charge of the 3O2 polyatomic anion. And the other most commonly occurring cation is magnesium, which is also 2 plus, so it will completely fulfill it also. Sometimes they share, so you have calcium and magnesium together. Very characteristic that the carbonates are forming in the tropics. So if you think about the tropics, it's the Tropic of Cancer and the Tropic of Capricorn and in between. So those two line, and the area in between those two is what we call tropics. Normally, when you go to any tropical island, such as in the Caribbean, you will see this beautiful turquoise colored water. When it's shallow, deeper water will be, of course, dark blue. So we're going to start with the limestones. When we have limestone, that's a so-called monomineralic rock, which means it contains only one mineral, almost 100%, and that is calcium carbonate. We will have to know 4 types of limestones. First one is the oolitic limestone, the coquina, fossiliferous limestone, and the lime mudstone. If you are going to be a geologist, you will have to learn different words, but for introductory class such as this 4 is good. As I told you, they form in the tropics between Tropic of Cancer and Tropic of Capricorn. So the first one is the oolitic limestone. The oolitic limestone is composed of ooids. Ooids are these low, round grains, and they are composed of concentric layers. You see how it's concentric? Of course, it's not perfect, but pretty much perfect. So concentric layers of calcite. It's usually white, beige, or gray. And the reason is because they always form in very shallow marine water, relatively arid climate, and you have to have vigorous wave currents. So as the wave is moving back and forth, if you had original low grains in the sea, the calcium carbonate, because it's arid, it becomes super saturated, so starts precipitating on that original low grain. And so that's why it's becoming completely concentric. So the most important thing that the oolitic limestone forms in arid climate, so it has to be no rain climate or rarely, and it has to be shallow, and it has to be high energy, means it's in the wave zone, high energy environment. The coquina is the next one. Now, the coquina is on the other hand, compared to the oolitic limestone, is composed of fragments, shell fragments, basically shell, coral, whatever is in the shallow marine environment, and it's also have beige or light gray color. What we don't have in the coquina is the ooid, so therefore it will form in areas where the climate is more humid. Because if it was arid, we would have oolites. But because it's more humid, we have the wave action, so it's a very high energy environment, and the shells are breaking up the ones who live there, so therefore it will become typical shell debris accumulates, and they are just being cemented together. So this is coquina. The next one is the fossiliferous limestone. What is really important about the fossiliferous limestone that it's limestone, and I haven't mentioned it, but we learned it before that when you have limestone, because it's calcium carbonate, if you put hydrochloric acid, which is in your kit, and it's not H2, it's HCl, it will become calcium chloride, and we need 2 molecules of that, plus CO2 plus water, balanced equation. So what you will see, it's CaCl2. you will see that the CO2, which as you know is a gas, will bubble. So when you drop the hydrochloric acid on the limestone, it will always make bubbles. So you can see it's fizzing. Fossiliferous limestone, you will know every limestone will fizz with hydrochloric acid. So you have to drop a little hydrochloric acid. If it fizzes, you know it's limestone. If you see fossils in it, you know it's a fossiliferous limestone. Now, the color of this limestone is pretty interesting because it has the fossils, and because it's a finer grain, that just shows you that the energy is not that high anymore. So it could form in open water deep down, but the energy is much lower. It's below the wave base, so there is no motion at all. So the carbonate mud is basically very fine grained. So if you don't have much oxygen, it's going to be dark. And if it's shallower, you have oxygen in the environment, then it will be much lighter. So the color is depend on the oxygen level of the environment. It's going to be in the tropics, and it's usually shallow or open ocean environment. It has to be below the wave base though. Okay, the next one is the lime mudstone. Now the lime mudstone is calcium carbonate. So again, it will fizz with the hydrochloric acid, and it's only very fine grained silt and clay sized particles. Don't forget that just the size, everything is calcium carbonate, so it will fizz really good with the hydrochloric acid. Now the color again just depends on the oxygen level of the environment. So it could be very light colored if it's oxygen rich environment, and very dark colored if it's oxygen poor environment. The next one we have to talk about is still in the carbonate group, but this is now a different composition. We call it dolomite. We learned it as a mineral in physical geology. The dolomite's formula is calcium magnesium carbonate. Okay, so when you have dolomite in the shallow marine environment, because that's where it forms, because it needs to be from pre-existing, it forms from pre-existing limestone. Therefore, it has to be forming exactly where the limestone is forming, which means in the tropical zone, usually shallow marine or deeper marine, it could be. And it definitely represents arid climate. Arid climate because when it's really drying up and the water evaporates, the calcium from the pre-existing calcium carbonate sediment will have to get out to make gypsum because it's arid climate, and therefore it will magnesium will have to build into the calcium carbonate, so it becomes dolomite. Sometimes they call it dolostone. So dolomite and dolostone are kind of synonyms. So it's the same thing. And they look like limestone, but when you put the hydrochloric acid, you have to scratch it before, and then even then you just see a little bit of fizzing. So you know that it's not completely limestone, because limestone is going to fizz very, very actively. The next group is the evaporates. The evaporates, as the name says, forming by the water evaporating out from the ocean, so it becomes more and more saturated, becomes super saturated, means lots of water went away, and we have more calcium and magnesium and sulfate and carbonate than what can stay in water. So therefore you start seeing evaporate minerals precipitating. Now they're precipitating in order based on their solubility. So the out of these evaporate minerals, gypsum is the least soluble, and the sylvite is the most soluble. So this is always going to be the order. The first mineral which will precipitate is gypsum. I wrote down the formula, but of course you don't have to know. The next one is the anhydrite. Then you will see the rock salt, the halite forming, and the very last one is going to be the sylvite. The sylvite has so high solubility that even the smallest low water content will dissolve it back. So it's not very, very often that you will see this whole sequence. So least soluble, most soluble. Most of the time you will see gypsum and anhydrite, and then much more rare is the presence of halite, and sylvite is almost never present. The next one is the chert. We learned the chert as a mineral, and this is the formula SiO2. Chert always forms during diagenesis. Remember, we learned diagenesis in the physical geology again. That is when the sediment will become sedimentary rock. During the diagenetic processes means that there is already rock there, and then something happens during the diagenesis. So diagenetic processes, most of the time, the SiO2 have very wide pH range where it can form. So it's either like 0 or 1 or and 14. So most of the time, when the evaporates dissolve, this chert will replace the evaporate. So many times you will see chert in the evaporate nodules like this here. Sometimes you can see whole layers of it. And in Virginia, where we are, a lot of the limestones from during arid climate, therefore they were full of evaporate nodules. Like if you think of Roanoke, do you guys know what was the original name of the Roanoke area? Yes, it was called Big Lick. Now, why was it called Big Lick? Because some of the evaporate nodules were still intact, so the animals could come back there and lick the salt. So that's why it was called Big Lick. The next group is going to be the coal. The coal, as you know, is combustible sedimentary rock, which is primarily composed of carbon. And of course, there are some other elements such as hydrogen, sulfur, oxygen, and nitrogen. They form from the accumulation of burial of plant material. Normally, it's in swampy, anoxic environment. Anoxic is when there is no oxygen present. So just imagine a coastal swamp. We have one in at Virginia Beach, so you can go and look at it. There is a boardwalk. You can see how the coal is forming. If you have a bay area closed off by a bay mouth bar, we learned in physical geology, then if it's humid climate like in Virginia Beach, behind the sandbar, there is the bay area and it's full of plants because of the humid climate. So we have basically forest in these areas. In the forest, the water is stagnant. It doesn't move. There is a lot of clay-sized material which settles down there. And when a tree dies, the tree falls off, goes into this water and gets covered by mud almost right away. Mud doesn't let the oxygen go through, so it's a perfect environment for coal formation. The sediment in the coastal swamp starts to get buried because new layers are depositing on top of it. Very soon, the carbon content of the sediment is becoming more and more enriched. Based on the carbon content, we divide the coal types into peat, the lignite, bituminous coal, and anthracite. The peat is the weakest. So the peat has about 65% carbon and 35% other stuff, which becomes ash. By this time, the lignite, it's going to be 75%. As it gets more and more buried, it has more and more carbon in it. 75% carbon, 25% ash. The bituminous coal, which is the most common in the Appalachians, so every coal burning power plant burn the bituminous coal, it's 85% carbon and only 15% ash. And if you have high enough heat and pressure, it's going to metamorphose. Basically, the anthracite is a metamorphosed coal and it has 95% carbon and just 5% ash. And we just finished the classification of the sedimentary rocks. And I'm finishing this segment, so we're going to continue with the stratigraphy in the next segment. I'll see you right there.